Welcome everyone. Thank you for joining this webinar. Today we will go into how to harness the power of decision intelligence. Before starting the presentation, a short introduction. My name is Joost de Lozerie. I'm a client solutions architect for Xylem Digital Solutions in Europe and will present today with my colleague Chris Harvey. Chris?
Hi, my name is Chris Harvey. I'm the Marketing and Development Manager for Wastewater in the UK.
Thank you, Chris. We will present our vision on reducing sewer overflows by actively controlling the urban wastewater network. First, an introduction to Xylem. We have 70,000 colleagues across the world that work together to bring solutions for water-related challenges to our clients. Our focus is to be the leading provider of intelligent water and infrastructure analytics solutions, digital solutions. We, as Xylem, span the entire cycle of water with our products and services. We move, we treat, analyze, monitor, and return water to the environment, serving the public utility, industrial, residential, and commercial building services sectors. To achieve affordable and resilient systems by making use of leading digital technologies, we have 6 strategies to target the challenges utilities are facing. These strategies are advance water equity, gain control of your data, reduce system losses, proactively manage your assets, ensure quality from source to tap, and manage the urban watershed. These strategies assist utilities in their digital transformation in a disruptive way. Today's presentation, we will go into more detail on the strategy manage the urban watershed. So, what's the problem? Nowadays, cities face an increasing intensity and frequency of extreme weather events. Meanwhile, most cities struggle with an aging infrastructure that was designed and built in an era when the solution to pollution was dilution. In other words, stormwater and sanitary sewage often flowed freely to urban water bodies by design. Increasing wet weather events also places a large burden on facilities treating increasing amounts of influent. As the amount increases, plant operators must increase operation costs to ensure effluent quality meets strict guidelines. The problem is that funding is not often available, which has a direct impact on the taxpayers, the citizens of the city. Current status to deal with these challenges are building large infrastructural networks and extending those if needed. The picture shows a big tunnel in London, and these projects are very costly. So with the limiting budgets, these must, could be done in a different way. The water industry and related infrastructure systems are trapped in a trilemma that will become increasingly unfeasible. In a trilemma, decision makers can only choose 2 of 3 competing goals. Today, water utilities are trying to maintain process stability and a risk-averse mentality, at the same time as trying to maintain the affordability of their services. This is unsustainable as populations rise and burden on existing infrastructure increases. The alternative to maintain process stability and increase system resilience will be unaffordable, as operating the same way while addressing growing needs will result in large rate increase that end users cannot afford. In the future, water utilities will inevitably need to maintain affordability while addressing the growing needs of their infrastructure. This will force major changes to the current way of thinking. To be disruptive, utilities will need to adopt approaches that enable better services at lower cost. What has changed in time and can be used to be disruptive? At the beginning of designing and building water networks in the 50s, the computing power was very limited. Within 70 years, computing power has 1 billion times improved, which gives us a huge opportunity, and it will keep on improving. It's really time for a new way. We have our BlueX platform that has its origin in 2004 that is disruptive to face challenges in the urban watershed in a new way. The name BlueX stands for Blue Infrastructure. The decision intelligence approach we use within our digital solutions goes by the methodology of sense, predict, and act. With sense as a first step to gather and integrate data into one source by collecting data from existing sensors, existing software systems, GIS, SCADA, etc. And in the next step, predict, we use the consolidated view of data to use artificial intelligence and machine learning to make predictions, conducting thousands of calculations to understand how the system will work when X happens, so that the best scenarios are established to your utility. Take action. Act. By having the predictions inside to make the right decisions before events like storms happen, so you can redirect excessive storms, water, and avoid costly overflows into streets, rivers, or body of water. I would like to explain our approach into more detail when it comes to optimizing the urban watershed and implementing the BlueX real-time decision support system, the RTDSS as we call it. BlueX combines the power of IoT, Internet of Things, big data analytics, and machine learning to unlock powerful new understanding of complex urban water networks, while dramatically increasing the performance, efficiency, and resilience of legacy infrastructure. Every utility has made big investments into SCADA systems, census models, and have an extensive experience in operating their own system. Therefore, it's crucial as a first step to sense the current situation by collecting and acquiring critical information to fully understand the needs and possibilities of the network. After this turn on the lights phase, we create a digital copy of the real-time situation in which models are used to put the data into context. With the predict phase, the neural networks is used to give insights into different scenarios by, for example, doing data analytics of the determination of anomalies. The final phase is the act phase, where the BlueX platform will act as a real-time decision support system to operate the network automatically and dynamically during the changing conditions that occur. The system changes the operation into a proactive approach where forecasting can be used for an optimal use of the capacity within the urban water system. As you can see here on the right, these are some examples of visualizations that we use, and they are used by clients currently as well. To give an example, I would like to share the case study of South Bend in Indiana, USA, where BlueX was founded in 2004. In the US, the EPA, which is the independent regulator, determines goals for cities to reduce overflows by stating a time frame to the city in order to solve the CSO problem. If the city fails to do so in the time frame, they will receive a big penalty. If they achieve the goal, they will not get a fine. This is an interesting approach where innovation is stimulated when budgets are limited. The city of South Bend has approximately 100,000 inhabitants, which decreased from 130,000 in the 60s after Studebaker, an automobile manufacturer, ceased production in the factory in South Bend. With the uprising storm weather events and the lack of financial options, South Bend needed to act outside of the status quo and be disruptive. They did this to start a program by partnering with the Notre Dame University and the state of Indiana. Lead of the program was Louis Montestruca, the founder of Mnet and our current president of Digital Solutions, and he looked for an alternative solution to solve the combined sewer overflow problems in South Bend by making use of advanced control system theory and civil engineering. Louis found it a very interesting task, and the start of BlueX was established. The following graph shows what has been achieved by the city of South Bend by using the disruptive platform BlueX. On the right axis, you see the cost of the capital infrastructural plans they had in 2004. As you can see, they had a plus $500 million plan. By using the BlueX approach, they only spent $10 million as shown on the left axis to date. You can see that it started with a proof of concept. Then, based on the needs of South Bend and the existing situation in the network of sensors, has been extended. 9 valves have been installed in 2011, and the control logic was developed. By making use of BlueX, we were able to do more than 100,000 capital infrastructural plan simulations, CIP, as you can see here, to find out what the next most cost-effective measure would be in the city to cope with the changing climate and environmental goals. Nowadays, we have an annual maintenance contract for years to come, which shows the long-term partnership with the city of South Bend that started already in 2004. I would also like to add that although this project started in 2004, today we can implement the full system in a year, and all the knowledge and developments are already available in the RTDSS, so the Real-Time Decision Support System. The visualization of the main interceptor from South Bend is shown here, going from the right above to the left downstream. And it shows the first stage of which is called the turn on the light stage in the sense phase. The green line which you see here is the precipitation, and the rectangular boxes are the manholes in the system, with the circles as the CSO valves in the system. By looking to the main interceptor, it's of course strange that although there is capacity downstream, as you can see here, upstream the water finds its way out of the system. In purple, the water is in the system, and when it gets pink, it gets out of the system. So there must be a reason why this is the case, and in the first initial stage, we want to find out why. And that's exactly what happened in South Bend, and by using one of our main automatic tools to accurately check the system sediment deposition, we were able to identify the locations of these potential blockages and send surface crews to clean the system. They find these kind of things in the system, and that's really in the first stage what we can do to clean the system and start from a good baseline. In the next stage of prediction, we create a digital twin that represents the real-time situation. This interface shows a map of the city on the left, and on the right in the graph, the calculation done by the swim model in the black line is shown as well. As you can see, the swim model identifies the events, but the model is not as accurate as you want it to be. There is no model that can be 100% accurate, but it is the goal to become as close as we can in order to be very precise. In order to do so, we are using our neural networks called CRIS. And CRIS stands for Cognitive Hydraulic Response System, shown here in the red line. CRIS is very accurate. To show this, one of our hydroinformatic engineers has visualized this time events needed to train the model. In this example, data from Kansas City is used. The graph shows the flow on the y-axis and the time on the x-axis, and the blue line is the measured flow, as you can see here. So after 5 weeks of training with 10 occurring events, CRIS identifies the peaks, but it's not as accurate as preferred. More training is needed, and after 12 events, 19 events, it goes on till 28 events and even 31 events, which stands for 15 weeks of training, CRIS is able to be very precise. The digital twin gives the user the possibility to run thousands of different scenarios to understand the system with this precision. The final unique step that we do with the real-time decision support system is to act by using our market-based optimization. The platform uses a multitude of network sensors and software agents to optimize operating gates and valves throughout the urban watershed. The software agents behave like stockbrokers in a stock exchange battering back and forward. But in this case, they are trading convenience and treatment capacity during a heavy rain, constantly rebalancing and optimizing systems to reduce peaks, avoid overflow, and flooding events to occur. This works in the following way. The agent at the CSO location knows based on forecasting that a lack of capacity is to occur and connects with the other agents to determine where he can bring his volume. The first agent tells him it will cost a fictive €5, the other 7.5 euros, and the storage tank on the right gives a €2 price. This will make the system decide to go for the cheapest option, as you can see here. So it will be pumped towards the storage tank, and capacity will be present at the CSO 30 location. So the result in South Bend of using Blue X is shown in this graph. With the blue line showing the increasing precipitation, we were able to reduce the overflow volume by 75% for less than 1/10 of the original budget. That's shown here with this red line. So you see precipitation increasing and the overflows are decreasing, and this is actually going to 2018. And I can tell you that still now it has increased even more, or the CSO has decreased, so to say. In addition, we also reduced the E. coli by 55% by treating more wastewater in the system before we had the chance to overflow into the river. One of the assets in the network could be a pump, and my colleague Chris will give you a more detailed explanation on the added value we can bring here. Chris?
Thank you, Joost. We're now going to step on to looking at the Concertor as part of the ultimate solution. So if we may step on to the next slide. Concertor actually is in a pumping station within the total asset. And the wastewater pumping stations form part of an overall network of sewer assets. Having intelligent wastewater pumping systems designed to significantly increase resilience and efficiency as a single asset with the capability of being controlled as part of the overall integrated network is the ultimate to prevent sewer overflow and internal sewer flooding. The Concertor hydraulic goes up to around 8 kilowatts in terms of traditional pump performance. In the UK, around 65% of the water company's assets are below 8 kilowatt. That's around 22,000 network sewage pumping stations. And out of that 22,000, approximately 50% will require 4 or more reactive visits due to pumps blocking. That's equivalent to around 44,000 potential risks of flooding per year. Our sewer networks are all too often abused, used as general purpose disposal units for non-biological solids, and this is the primary cause of pumps blocking. The following slides demonstrate how intelligent the wastewater pumping systems can take on these challenges and succeed. Key to resilience is the ability of the pump to handle the non-biological solids. A combination of impeller design that cleans the leading edges on every rotation, the ability of the impeller to lift to allow the larger solids to actually pass, and a motor that delivers high torque across the speed range and onboard intelligent functionality and power electronics that read the data signature indicating potential blockage and then runs a very precisely controlled sequence to maximize the chances of the pump passing the rag. Here we have the Concertor being demonstrated in the video. There we go, passing the rag. Clean sump functionality ensures such things as fats and solids are transported through the system efficiently and frequently, so reducing the chances of solids building up to a size that may cause a pump to block. By initially starting the pump sequence at full set performance, ensures the non-return valve is actually fully opened and the settled solids become agitated, ready for transportation. Also taking the liquid levels frequently down to low level or snore as part of the clean sump technology improves the condition of the wet well. Sump cleaning functionality reduces the requirement for using cleaning tankers, which in turn reduces the disruption to the general public neighbouring the pumping station and saves around about £1,000 per cleaning visit avoided, so lowering the operating cost of the station. This is a typical example of what we have with Concertor. So if we look at the picture to the top left-hand side, that's before we fitted the Concertor system, and to the right is a year after. The pictures to the middle, this was a station that was particularly problematic, high levels of fat. That station was being cleaned out frequently and actually had been cleaned out 3 months before we took this photograph. We cleaned it out and put the Concertor system in, and the picture to the right of that is the station a year later. So it's clearly keeping the station nice and clean. And the one to the bottom of the slide is a picture showing the floating rag mass, and to the right-hand side, the actual reduced amount of floating material. And that was the first phase of actually putting the Concertor system in. So the one on the right-hand side has actually only got one Concertor XPC system in. So it's doing rather well. Now, obviously, it would be better if there's two, because by alternating duty, you clear the complete chamber of material. Thank you. Most wastewater pumping stations have an underlying diurnal inflow pattern, and that's aligned with population movement. So the peaks normally occur in the early morning and then in the early afternoon, with lower inflows during the rest of the day. The vast majority of pumps in wastewater pumping stations are a fixed performance and sized to cope with a maximum inflow plus a generous engineering safety margin. Pumping the maximum flow through the pipework, especially long rising mains, burns a significant amount of energy as you incur the maximum amount of friction in the pipework. This also has the pumped rising main running at full stress load for the duration of the pump cycle. By using intelligent pumping systems that self-learns and varies the pump flow to operate at the best efficiency point of the station, but also accommodates for increase in inflow as it occurs, is pivotal in lowering the electrical costs, carbon footprint, and reducing the risks associated with fatigue on the rising main. So here we actually have an animation which shows how Concertor learns a pumping station. So if we look at the top graph, we've actually got a line that looks a bit like a mountainous profile. It's got a triangle on it, and that's the volume. So the lower left-hand side, what we actually have is a graph which has got a curve to it, a bit like a U, and that shows the speed relative to the kilowatts and volume pumped. The best sweet spot for that particular station is at the lowest point of that curve. And as you will see, Concertor is adjusting its speed to accommodate not only for the increasing inflow, but also trying to hunt that best efficiency point, self-learning the station's best efficiency point. So once we go through this once again, it will be a moment. You'll start and see that Concertor actually starts its performance at maximum speed. Then it slows itself down, and then if it sees an increase in volume, it will increase its speed to beat that. It continues down the path to best efficiency point for that particular station. You'll see an increase in volume again occurring just about now. You'll see Concertor speed up again. And it will actually progress, and it gets to the point where it knows the best efficiency point and passes that. So it knows it's slightly less efficient, and it will come back again. So it is actually learning the station, but it constantly reviews that. So it will constantly change to best efficiency point if the rising main changes, the condition of the rising main. So it's constantly on vigil to ensure best efficiency and also to beat the current inflow volume. Thank you. Data. Data is fundamental in running an efficient, resilient wastewater pumping asset. This data allows the end user to identify the asset by serial number, monitoring condition and performance, which is key to a proactive maintenance regime and reduces the risk of flooding as a result of critical failure. Further, as part of the RTDS, that's the real-time data support system used in BlueX, live data such as current pump performance, available additional performance, wet well level, anti-clog trends provides critical information to enhance the system's ability to make smart decisions. Concertor wastewater pumping system targets all areas of the challenge that the utilities face in a single asset. delivering significant resilience in the battle to prevent local flooding and discharge of sewage to watercourses. The Concertor system operates as a standalone, but is also a team player, and when required, integrates into the BlueX intelligent network system that can instruct a change in performance in accordance with the needs of the network to prevent sewer overflow and sewer flooding. Thank you.
Thanks, Chris. So yeah, as Chris mentioned, so the Concertor is really one of the assets in the total network. That's the combination we want to show here. And then the Concertor could help, right, going back to how we operate the system to automatically transport the wastewater to the storage tank in our market-based optimization. So our goal is really to provide the most intelligent water-related digital solutions to our clients, as mentioned in the beginning. We prefer to work in a partnership with our clients, which creates the most valuable outcome. We can discuss with you and key stakeholders at your utility during workshops how decision intelligence can help address your most pressing problems. Based on the workshops, we can work together to tailor a business case to ID cost savings, revenue opportunities, and risk reduction impacts, which you can use to discuss with internal and external stakeholders. Our team can meet with you, internal and external stakeholders, to provide our perspective on the rationale for adopting decision intelligence. We understand you often have limited bandwidth to execute initial deployments that are new to your utility. We offer full-stack turnkey solutions that include physical equipment, installation and integration services, training, maintenance, and post-deployment support to help your organization implement without the distraction from daily work. How do we start a project, and what's the effort required for you as a utility? We are happy to get in contact and discuss the challenges you face in your system. The reason for this is the conversation and to talk about and fully understand your needs and to specify a discovery project. During this discovery project, we analyze your current situation, and within 10 to 12 weeks, we organize a final workshop together to discuss our findings. The process is a collaboration with the utility, independent of the SCADA system, the sensors, or models used. We would only need the problem statement, for example, optimization of flow towards the wastewater treatment plant, or reduce CSOs in a selected area. And we would need GIS layers and the hydraulic model that is used to start the process. So that was what we wanted to share today in the presentation. We want to thank you for your time, and we will close by emphasizing that this is the time to act in a disruptive way to the water challenge that you are facing. Please feel free to reach out to us. Emails can be seen here below on the slide. And we are really happy to work together with you, and we look forward to work with you in a disruptive way. Thank you for your time.
Thank you.